Boeing has always been part of my life. My dad works at Boeing. He's worked here for his entire career.
I'm a second-generation engineer.
Both of my kids fly Boeing platforms. One flies F-15s and the other one flies C-17s.
I'm a third-generation Boeing employee. My grandma and my mom both worked here.
I'm third-generation Boeing. My grandpa worked here, my mom, my dad, my uncle, my cousin, quite a few people in the family.
It takes a real team to make progress, but it has to be balanced with a culture that's respectful and with people that truly honor each other.
The culture has, I would say, ebbed and flowed, and there were times where it was really negative and really down, and quite honestly, the past few years, that's how it's been.
Boeing's culture today is changing. It's not there yet, but the culture is definitely on the rise.
I think we've got work, but I see the right trends to get the work done.
You see a lot of people that still have questions about where we're headed, and you see a lot of people that know where we're going and are really driving that change. And so we're a work in progress, but I'm so excited for where we're headed.
When I saw the new Boeing values and the behaviors, I was enlightened. Before, it just seemed to me like putting stuff out there on paper, right? These ones actually resonate with, I think, a lot more people, and myself included.
I see so many people with their values and behaviors printed out at their desk, and we speak about it not like this is Boeing's values and behaviors, but this is our values and behaviors. So I think it's just brought everybody together.
We need to see our leaders actually living and breathing these values, because if they are, then that is inspiring the next generation of people coming into Boeing. We don't want leaders that are just sat there being a bit stale and they're not kind of leading in the way that other inspiring leaders are.
Especially in the last year, we do see quite a bit of difference. There are a lot more interactions between the upper management of the company as well as the individuals within the organization.
The one thing I would offer to our leadership in this company is don't ever give up on this. It is a perishable thing. People need that motivation. People need that confidence that what they're doing is important.
Listen to your employees, the ones here on the ground floor, the ones building the product, the ones that are neck deep in all what goes in on these airplanes. They want to do a good job, and they have good ideas. They have great suggestions. They bring so much to the table.
The ability of our teams to look out for each other, to respect each other, to be courageous, those are the things that are going to help our culture turn the corner.
I think because we've been in such dark times, there is this lovely light that I can see in the future that's going to change things and just drive positivity within the teams as well. It's a great future ahead of us.
Good morning, good afternoon, and good evening to Simio Sync 2026 participants. It is my pleasure to participate in this annual conference where practitioners and thought leaders share how they used Simio to gain insight and solve problems. Paint facility sizing for commercial aerospace manufacturing is a project about capacity of an existing system as demand changes, and will answer questions like, when will demand exceed capacity? If the system was built new, how much factory is needed? My name is Chris Tunn. I have 30 years of experience in general, military, and commercial aviations. I have served at 4 companies in engineering, management, and continuous improvement roles, and I provide discrete event simulation, capacity planning, and project management services at Boeing Wichita in the Core Industrial Engineering Group. Randy Allenbach collaborated on this project. He has had a distinguished 40-year career working in military and commercial aviation with Boeing and Spirit Aerosystems. He is an associate technical fellow, provides leadership, expertise, and mentoring in the development of discrete event simulations, i.e. strategy, simulation standards, analytics, technology development, and decision support. For 20 years, he was an adjunct lecturer in simulation at Wichita State University and made a significant contribution to the discrete event simulation profession. Now, a quick overview of the Boeing Wichita facility. Boeing Wichita has a long history beginning in the 1920s. It played a vital role in World War II, producing over 1,600 B-29s and later 744 B-52s. In 1967, the first 737 delivery occurred, and production of the 747 began. In 2018, the 10,000th 737 fuselage is produced. Today, Boeing Wichita produces aerostructures, which are large components of aircraft. that are shipped to Boeing and other customers for final assembly. Boeing Wichita participates in commercial, defense, and aftermarket aerospace business sectors, and specializes in design and manufacturing of high-rate metallic and composite aerostructures utilizing state-of-the-art machining, assembly automation, and composite fabrication technologies. It has world-class engineering capability supported by a dedicated research and technology center. Commercial is the largest division with over 13,000 Boeing employees and 1,700 engineers and technicians. They produce parts for the 737, 767, 777, 787, and P-8 and KC-46 military variants. Spirit Defense has 1,500 employees with 500 engineers and technicians, and produce parts for the B-52, B-21, CH-53K, and other undisclosed programs. Global Services supports aftermarket and maintenance, repair, and overhaul of radomes, nacelles, and wing components. Now that you are familiar with the Boeing Wichita site, I will focus the remainder of our time on the paint facility capacity study. This project had 3 questions for the modeling team to answer. Can existing facility meet future demand? If not, when will the demand exceed capacity? If a new paint booth technology were deployed, how much paint facility will be required? The system paints engine cowlings, thrust reversers, and inlets, or the outside visible parts of a commercial aircraft engine. 3 aircraft models are painted in this system. Each model family has approximately 20 parts. Each model has its own independent production rate, measured in aircraft per month, or APM. The system is complex, as there are unique part routings where some parts loop through the paint step multiple times, unique process duration for each step and part. Each part has its own rework likelihood. Normally, parts are produced individually, but batching 2 parts together is possible if they are of the same part type and finish, arrive within 1 hour of each other, and both parts fit in the equipment being used. Part due dates set the priority when 2 parts simultaneously need the same resource. In the paint booth, painting begins only if it can be completed before the end of the shift. In addition, 1 part family is going through a model change where the new parts are significantly larger. To provide some scale, there is a person right here in front of the engine. As you can see, this engine is quite large. The model is also changing the paint being applied, which requires 2 trips to the paint and cure steps. Both of these changes add capacity pressure to the existing system and contributed to the complex nature of the project. Traditionally, Excel-based capacity studies are used. They work well when focused on a single type of equipment, but do not handle complicated routings and batching behavior well. They have no visibility to buffer sizing and cannot predict on-time delivery by part. Discrete event simulation, on the other hand, can handle this complexity, can include special processing rules, perform what-if scenarios, and can score each part and system performance. I like to think of the discrete event simulation model as an input, process, output chart. Inputs are the information about the system that may change, such as demand, part routings, worker schedules, part durations, and rework likelihood for each part. Process section describes the system, which includes how demand is converted to a part arrivals in the model, custom processing rules like when is it okay to start a painting operation, resource availability, and part movement delay. Outputs are how the system is scored. For this project, on-time delivery percentage, past 2 days, equipment and worker utilizations, space consumption log, and a number of parts in the system graph. This project has many assumptions. A few to point out are: some parts can be batched and others will never be batched. Each part has a little different footprint and consumes a different amount of square feet. These differences are accounted for in the model. We also accounted for the additional square feet that are consumed at each step of the process. There are available time differences between current state and future state. Part arrivals occur at midnight each day. In the future state, first shift starts at 6 a.m. Part movement between steps require 10 minutes per part. Two models were created to answer the project questions. A current state model focused on the existing system of sand, wash, paint, cure, and general part buffer used for each step of the process. This equipment was sized for product and demand in the 1980s and 90s. Current state conditions in the model include batching can occur for smaller parts, but typically doesn't due to low production rate. They simply don't arrive to the paint system at the same time. With the model change mentioned earlier, part sizes increase to the point where they just barely fit in the existing equipment. These size constraints make batching impossible for those parts. A new paint material and curing requirements for the new model dictate these parts loop through the painting and cure processes twice. Increasing demand in combination with these two changes has increased the capacity pressure on the current system. Well, of course, the current paint booth and oven were included, and to examine max throughput, an additional paint booth currently used for training was included in this current state model. To score the current state model, we used a graph called number of parts in the system. This graph will increase by 1 for every part that enters the system and decrease by 1 for each part that leaves the system. The flat portion of this graph indicates a steady state system that can process the part arrival rate. The sharp positive slope indicates when the system is no longer able to keep up with the increased arrival rate. This means the system capacity has been exceeded. The x-axis is time, so we also have a prediction of when that will occur. The red arrows superimposed on top of the graph indicate the new model's APM demand, or part family's arrival rate. Note that the system becomes unstable between the increase from 1 APM to 2 APM. One of the ways the current state model was validated was to compare the Excel-based load chart with our model's prediction of when capacity would be exceeded. We found, with a few assumption modifications, that demand would exceed capacity of the existing system at approximately the same times predicted by the Excel load chart. The assumptions changed in the current state model were no overtime, no rework, and no additional primer flash-off time due to humidity or temperature. This current booth uses outside air that is not conditioned. Therefore, there are times during the year when they are not able to paint, or it takes longer due to environmental conditions. Note that the Excel load chart used part standards with no variability that overestimated capacity. The model used subject matter expert times with variability, which more accurately represent the current state process duration. By comparing to the Excel load chart, we learned how the model differed from the traditional capacity study methods and learned about their limitations. We ran many iterations of this current state model, all looking for ways to extend the capacity. One included enlisting a retired paint booth relegated to training new part painters back into the production service. This booth had many limitations that were included in the current state model, including part size. None of these iterations were enough to satisfy the increased demand. Therefore, we were certain that the future demand will exceed the current state capacity within a known time frame. For the future state model, the customers wanted to know what a greenfield building expansion paint facility would look like. In short, how much paint facility is needed to accommodate future demand scenarios, assuming The same part routings, durations, and rework rates are used from the current state model. 2 shifts, 5 days a week would be the available time for the future state model. And new equipment would be sized to batch 2 of any sized part throughout the entire process, meaning there really wouldn't be any equipment size limitations, minimizing batching. Also of interest is how beneficial will batching be of parts? I mean, does it have any useful reductions in equipment? The customer shared that new paint booth equipment can both paint and cure in the same physical space and was wondering, is there any advantage to that? So we designed a system with the theory of constraints in mind, meaning we wanted to decide where the constraint will be. In this system, the constraint will be the paint booth because it is the most expensive equipment and requires the most skilled labor in the system. Therefore, we want to minimize that piece of equipment. All other steps will have more capacity than paint so that they can always keep up with paint, or if they fall behind for some reason, can catch up to the constraint. Parts will be pulled from the arrival holding buffer through sanding, wash bay, and masking, and pushed through the cure and demask, stencil, QA, and staging for ship. When a part leaves paint, the next most urgent part will move forward and take its place. This same principle is applied all the way back to the holding buffer. When a part finishes being sanded, washed, or masked, they will simply stay in place until they are pulled forward. All a team lead must do is decide what is the next part to start from the holding buffer when the next part finishes paint. So it stays pretty simple. To evaluate the solution space, the following test methods were applied to the future state model. There were multiple demand scenarios to test. A scenario consists of 3 part families, each with their own aircraft per month program rate. Programs A and B had fairly steady future APM rates, but Program C had multiple demand levels to test. For each scenario, the demand was held constant for all 3 programs for 12 months. That was enough time to see how the method and equipment quantities handled the demand. Next, we would set the method, with or without batching, and cure in an oven or curing in a spray booth called a SPUVN. Set the equipment quantities, and then run the model. Record the results, and then iterate until you found the least amount of equipment needed to meet a demand scenario and method combination. Repeat the process until all demand scenarios and method combinations are tested. It is important to quantify a scenario's effectiveness to achieve a production system goal so that multiple scenarios can be compared with each other. To quantify our future state model's effectiveness, each part is assigned a planned flow days, or PFD. This came from our ERP system. Each part entity records its model flow days, or MFD, or the time in the system. Each part entity in the model is scored, where on time is when the model flow days is less than or equal to the planned flow days, and late is when the model flow days exceeded the planned flow days. To score model scenario, we used 2 methods. We calculated the percentage of on-time entities, and we took the total past due days, where we simply totaled the difference between the modeled flow days and the planned flow days for each entity. In general, if the program rate and equipment quantity were held constant, but changed the methods, it was found that batching with oven cure performed the best, and no batching and SPUVN performed the worst. Currently available on the market is a paint booth that can double as an oven called a SPUVN. An open question for this project was to consider which part curing option was most advantageous, paint booth and oven versus a SPUVN. Traditional Paint booth and oven combination allows the paint booth to be used for the next part when the preceding part leaves the oven. Here you see the paint staging step in this little flow chart here. The parts go to paint booth, then the oven, and then stage for ship. So as parts leave the paint booth, they can move to the oven and another part can come into it. A spoven uses the same equipment and space to both paint and heat cycle the part. So there is no oven step here. They just go to the spoven, they do both paint and cure, and then they go to stage for ship. The pros of oven cure is that work can flow from paint to cure and require less paint booths, but requires higher equipment count and square feet. Pros of spoven is that it eliminates the part movement between painting and oven and requires less amount of square feet needed. The con is that the painters must move between booths. The Gantt chart here shows some of this activity. In this highlighted area, you will see in the paint booth and oven example, as soon as the part is painted, the painter then leaves and after they've moved it to the oven, and then the oven does its job, and it makes the paint booth available for the next part. Whereas in a spoven, they do the painting operation, they stay there, the painter leaves, there is no move operation, and then the oven cures the part. It was of interest to know if there is a real equipment count difference between batching parts versus not batching part method. I will provide some context on how this was tested. The time to paint batched parts is longer than a single part, but faster than painting two parts sequentially. So there's a little bit of an advantage there. The test compared batching everything that can be batched in a scenario or batching nothing at all in another scenario. Batch size is defined as two like parts, for instance, like a left-hand part and the same right-hand part with the same finish. For non-painting operations, each part has one person assigned to each batched part and work in parallel. Each part in a batch gets its own unique variable duration. Both parts must complete before they can be moved to the next step in the process. For example, you see here in the Gantt chart. On top you have a non-batched part and it's just moved once completed. And here in the sanding operation, you can see that there are two parts. One took distinctly longer than the other. The one that's done first is held until the second was done, and then they're moved together to the next operation. Time to move a batch part is 20 minutes versus the 10 minutes, and you can see that in these little vertical lines here. This is a 10-minute move, and this is a 20-minute move. As I had mentioned earlier, to batch parts, they need to arrive in the paint system within about an hour of each other. And we wanted to build that into the model. And so we went on ahead and did that and got that functionality included into the model. However, in the end, that hour level data was not available. And we couldn't use it. We couldn't use that new functionality effectively. We wasted our effort putting that into the model. What we did have was arrival data based on the day, so we could predict when a part might arrive on the day level. And so in this model, what we did was we had all the parts arrive at basically midnight that would arrive for that day, and then we would process them accordingly. During model reviews, a concern was expressed about the level of rework for the new model parts. As mentioned earlier, they have a new to this paint shop two-step process. They thought the rework rate would increase from their past performance because the part quality expectations were going to increase. Various levels of rework were tested for just these parts to understand their potential impact on equipment quantities. The baseline rework rate was 5%. Tested were rates from 0% to 25% in 5% increments. At 0%, they had no equipment changes from the 5% settings. That kind of makes sense. At 10%, an additional oven and paint worker were needed. At 15% and 20%, the system needed that same 10% adds plus an additional paint booth. At 25%, we needed a total of 2 more paint workers, 2 sanding booths, 2 wash bays, 1 paint staging location, and 2 more paint booths, and 3 more ovens over the baseline 5% rework rate equipment needs. Basically, the wheels had come completely off the process when rework was at 25%. So one can conclude that the rework rate for these new model parts were significant in setting the equipment needs. One of the advantages of a discrete event simulation capacity analysis is the quantification of buffer size. Each part consumes its own amount of square feet. At each step of the process, an additional space is needed to perform the work properly. For example, in an oven, they need 2 extra feet around the part for proper airflow. In many of the manual steps, 3 feet around the part is needed to make room for the portable stairs. In a wash bay, 6 feet is needed around the part to operate a pressure washer wand. Simio kept track of how much space was needed at each step of the process, especially in the staging areas, so that the proper amount of square feet could be allotted to them. Future state model results. There were 4 different demand scenarios tested in each of the 4 methods. Here you'll see Program A, Aftermarket, and Program C. And Program C had 4 levels of increasing demand from left to right, where the highest amount of demand would be this final column right here. Each of the 4 methods were also shown here: batching in oven, batching in spoven, no batching in oven, and no batching in spoven. Each demand scenario and method combination was scored with a % on-time delivery score, where 1 represented 100% on-time delivery, and something less than 100% would be represented as something that was less effective. So here, in this situation, where you've got an oven, no batching, 5 paint booths, and 3 ovens, the first 3 levels of demand were successful at 100% on-time delivery. But then the 4th, the highest demand, had less effectiveness. For each method quadrant, the number of paint booths and ovens were totaled. Batching and oven combination required 4 paint booths and 3 ovens for a total of 7 pieces of equipment. Batching and spoven required 5 paint booths and 0 ovens for a total of 5 pieces of equipment. The results were that a spoven curing requires 1 more paint booth, but 2 fewer equipment as a system. Very nice if square feet is at a premium. Batching requires 1 less paint booth than not batching. These are very interesting results, where on the surface, maximizing the flow through a paint booth by using a separate oven cure seemed like an obvious design choice, because it minimized the expensive paint booth equipment needed. But when the entire system is taken into account, it is better to use spoven technology because it uses less equipment as a system and reduces the overall square feet needed. Project conclusions. The existing current state equipment is not sufficient to meet demand. Leaders were informed when issues will begin and the effectiveness of short-term countermeasures. Facility engineers were provided a range of equipment and space requirements needed to meet future demand in a greenfield building expansion. These recommendations were used to size and cost a building expansion. Ultimately, space was at a very high premium, and minimizing equipment count was attractive as well. The spoven approach to curing was adopted. All equipment was sized to allow the batching of large parts. Simio was an effective tool in identifying that the existing current state system could not meet future demand and predicted when that would occur. Discrete event simulation is a superior capacity analysis tool than Excel for complex systems because it can handle complex part routings, rework rates, quantify buffer sizes, adds duration variability to the analysis, and can evaluate the system versus a single piece of equipment. Thank you for the opportunity to present here at Simio Sync, and I will take any questions. Hello.
Chris, good afternoon.
Hello, Drew.
Great presentation. As I say, I
Thank you
think
very much.
excellent to see going from problem statement to methods to results. So great job. And we've got plenty of questions to go through, so we'll get started. All right, first one. Can you expand on some of the major considerations of modeling out the current state of a facility versus modeling out the future state?
Yeah, sure. This question around current state capacity had been around for quite a while. In fact, back in 2019, 2020, we started working on this model with a person who now works at Simio, Rylan Carney. He was an intern and co-op student here at Spirit Aerosystems at the time. We're now Boeing, uh, and he started working on the current state model. Conditions changed. That program that was kind of pushing the pressure changed, and this question went on the back burner. And then now we picked it back up again last year. So some of that current state work was done by Rylan Carney. We certainly want to give him a shout out and appreciate his effort on this system. So one of the big questions we had about the current state system was, well, how long would it be effective? How long, as demand changed and the mix of the parts and the size of those parts changed, how long would the current state system be effective? And so that was the main driver. And then at that point in the project, they were also strongly pushing for like a greenfield building expansion type approach, and they wanted to know how much uh, capacity or how much paint facility would we need in that situation. And that's what the future state model did for us.
Got it. Yeah, I would say probably working with current state and some of the historical data to go off of probably helps to make some of the validation work more effective there versus probably have to make some assumptions along the way with the future state and greenfield and things like that. But a lot of good insight there, and I'm sure Ryan will appreciate the shout out there.
Yeah, we absolutely use the same data set or inputs when it came to processing times, durations, routings, as far as the steps, what steps of the process it needed to go through. Of course, with current state, it used existing equipment, and with future state, it had that different layout of the process flow and some different operating rules. But yeah, we definitely use the same durations and rework rates, things like that.
And were there any spuvins in the current state, or is that would all be future proposal work?
Yeah, that was all future expansion because there was no spuvins in the current state. Yeah, that's technology that's come along since the implementation of the current state equipment.
Yeah, I'm sure that's more sophisticated than the spork. The spuvin probably has a little bit more nuance. So we'll keep going. All right. So what stakeholders are involved at Spirit when you're reviewing the modeling needs and determining what assumptions are appropriate to make or not?
Yeah, so we were requested at a fairly high level. The manager of the program was wanting to have a model created so that we could answer these big questions, right? How long will the current state system work? And when do we need to do something to add capacity? And like how much of a new system would we need? And so uh, they got input. The plant leader the person overall, the execution portion of the process, they were involved. And then, of course, uh, first level leaders, uh, t- uh, team leads, all were involved, industrial engineers that support that area. And they all had input into it. So to give you some example, there was one requirement on the future state model that came directly from that top level leader that said, I want you to model this with an available time of just 2 shifts, 5 days a week. I do not want you to use third shift. I do not want you to use weekends. I want to know how much pieces of equipment we would need, how much facility would we need under those conditions. Whereas on the current state, they're like, well, we're ready to do whatever we got to do to maximize its usefulness. So they were testing other available times, like 3 shifts.
Interesting. Yeah, I was saying, I'm sure getting those voices, you don't want to operate in a silo when making your assumptions. You want to make sure that you're getting all those voices of the customer understood before landing on what your approaches may be. So sounds like there's plenty of input there. I'm sure it's a large effort to get the scope fully defined.
Yeah, one more. The team lead mentioned about the approach that they take about whether we'll start the next part in the paint process. They're very particular about who does all the paint work, and if some work was to go over a shift, um, uh, they would delay the start of that part so that two people didn't have to paint that same part. So they want to have one painter on a part at a time. So there was some challenging logic there to try to figure out how would you do that evaluation, add a constraint, and implement that into the model. But that one came a little late in the modeling phase, and we were like, oh, okay, here we go. Let's figure out how fast we can figure this out. So yeah.
That is the joys of modeling of new constraints added in is never linear as much as you'd like it to be.
For sure.
All right. So how do you decide if you need to model something as a target versus a firm constraint? And it seemed like when you were modeling out your current capacity, you used that current capacity as a target versus a maximum value.
Yeah, the current state, I would say, is we had a certain amount of equipment. It turned out we had mothballed uh, a paint booth that was used for training. It was done that for a reason. It really can't hold as much. Parts are pretty large. There's a lot of limits as to what that piece of equipment could run. But when it became obvious that they needed additional um, capacity as much as they could, they're like, well, what if we pull that back out of the training use and start using it for production again? We had to add all those constraints to the system to see what that impact would be. I would say in the current state approach, we used it more as a as a constraint rather than a target. At least the way I'm understanding the question here. Um, and then we really didn't in the future state. We didn't think of it as we were trying to get to a certain number of pieces of equipment. It was more how many would we need, understanding the flow and the requirements of the paint system, the levels of rework, the process duration, so on and so forth.
Okay. Yeah, I would say hopefully that was um, along the lines of how they were perceiving that question, but like the thoughts there. So you mentioned some, and you just mentioned with the operator, the team lead. So if you have multiple parts competing for the paint booth at the same time, how do you decide which part will ultimately get the resource?
Yeah, so every part has a due date, and uh, painting is tends to be towards the end of the production assembly process. So they're very mindful of those due dates, and so they will start the part that has the most urgent due date, the one that's closest to that particular moment. That's how they break those ties.
Okay. Yeah, I'll say that. I know there's a lot of different ways you can consider, but that one makes it pretty clear.
Yeah, and Simio makes it pretty easy to use that feature. I mean, we just throw it on as a state variable for the entity, and then when it's evaluating the queue to run next, you can run some. There's some opportunities to, let's say, minimize or maximize some value, and we looked at that. We looked at that date.
Yeah, I feel like often there's the trade-off between running things that have the earliest due date versus are we going to incur a penalty from a changeover as a result, and kind of balancing that batch sizing, campaign sizing versus due dates. A lot of different instances of that. So much in the same vein. All right, let's keep it rolling. So how did you go about adding in certain batch behaviors like the 1 hour holding area constraint? Are there some approaches that you found more valuable than others?
Yeah, that was a challenge. One of the ways that we learned to batch parts was to put a ride station on the entity, and so one entity becomes kind of the parent itself, and anything that we want to batch with it, we throw in the ride station of that entity. So every entity that's going to be running through the system has the capability of being the parent or the child situation. And so what we did was, as parts entered that initial queue, that initial arrival queue, it would search to see, or when I hit the node, it would search to see if there was anything in the buffer. And if there was something that it could be batched with, then it was moved to that particular part's ride station, and then they moved forward together. So that was a pretty unique approach to batching, using an entity to be the parent, rather than using a batching, um, you know, uh, object.
Mhm.
And we've leveraged that method several times over here at Spirit Aero Systems for different situations, and it works pretty well.
And I guess with your batching, were there other conditions beyond the part number? Did they also did they both have to be new parts versus reworked? So I imagine there's probably some other things you had to consider of what can be batched beyond just maybe the presence of the hour or not.
Right. Well, we made the batching decision up front where new parts arrived. So, kind of generally speaking, if something got reworked, it was on its own.
Okay.
It was in a hurry, so it's going to be moved through on its own. Um, and so when parts arrived, that's when we would make that batching decision. There was a constraint involved in there to limit how long a part might stay in the queue to be available for batching. If it exceeded that, then it would move forward. Now, I mentioned in the presentation that we did all this effort and modeling to do the batching, and this 1 hour buffer, uh, in hopes that the data would become available. It ultimately didn't become available, and so we ended up having to test basically the two extremes. You either batched everything that could be batched, meaning things that would have arrived that day, um, and if they arrived at midnight, they would immediately look at each other and go, "Oh, hey, we're we meet the conditions that would be to batch," and then they would proceed to be batched, or we turn batching off, and everything would be processed individually. Now, what were some of those other conditions? We used it was known about which parts could be paired with each. So in an aircraft, you have a left hand and a right hand part for the different sides of the aircraft.
Mhm.
If they are of the same uh, uh, let's say it was the same part of an engine cowling. They have the same finish, of course, meaning the same type of paint being applied. Then they could be batched together. There were situations in the current state model that parts couldn't be batched because of size. They were just physically too big, and so we would turn those things. Uh, the data that would come in from an input table, um, would show that those things couldn't be batched. And so we had a number that that would indicate, hey, these parts could be batched, and they would look for that number as an attribute on the entity, state variable on the entity, and they say, hey, if we match, we can batch. If we don't match, we can't batch.
Okay, got. I was saying that the part of the sizing of the parts is interesting because I mean that's in traditional simulations it's usually kind of unit based capacity of a server has 5 units. Where in this case, obviously each part has a set of box dimensions. It seems that can make that constraint more dynamic. So from a modeling perspective, that's quite interesting. So you talked a little bit about the recommendations. Is there a greater burden of proof for stakeholders to recommend CapEx proposals like purchasing a SPUVN versus a policy change like enacting batching?
Yeah, SPUVNs had been purchased by our organization before. They have some experience with them, so it wasn't completely new technology. So we didn't necessarily feel any higher burden of proof needed. There was skepticism that a SPUVN where you would paint and cure within the same physical footprint and space of a piece of equipment would be the most advantageous use of space and capital. And so that's why we tested it in our model to find out, hey, do you need more paint booths, and if so, um, what's that cost? But uh, as it turned out, you actually have less overall pieces of equipment and less square footage needed by having SPUVNs versus SPUVN or a paint booth and an oven combination. And so, yeah, I found that to be a really interesting insight. Now that worked for us in our situation and our durations and so on and so forth. And it may not apply in all situations, but it did in this situation.
Yeah, I feel like that's unique to the relationship that the modeler has with the stakeholders of if you're making these recommendations, you want to know that you've gotten that stakeholder buy-in throughout the process and these recommendations are coming from a known source. So probably like you said, you've worked with them for plenty of time, so I'm sure there's plenty of trust there of your recommendations are coming from a known source.
Yeah, those new pieces of equipment also had the ability to condition air, meaning they could make it warm enough when it's really cold out and dry enough when it's too humid out, cool it off. So yeah, that was a nice advantage and uh, allows you uh, to to paint and plan to paint regardless of conditions outside.
I'm sure those Kansas winters can get pretty brutal.
It gets pretty humid here too.
It's much like Pittsburgh. If you had visibility to see when parts will actually arrive, how might that change your approach for batching, if at all?
Yeah, I mean, we we tested the both ends of the continuum, right? Batch everything you can or batch nothing. If we could have had more granular information about when parts arrive, then we would have been able to test in between those two extremes and have a little bit more understanding of what that impact would have been.
Okay. Yeah, I was saying you elaborated on kind of some of the planning for the possibility of that data. So, um, yeah, that sounds like that would have been a key point of information to have. All right. I think we got a couple more here. And similar to the question that was asked a little bit ago, when sharing recommendations with stakeholders, are there certain views or metrics that you found most effective to make your argument?
Yeah, doing that comparison on the SPUVN uh, cure versus an oven cure, that was really eye-opening. You know, the folks that were speculating that the paint booth and oven combination was a hands down winner. Um, that speculation tended to go away after that comparison, so that was really interesting. Um, it's very obvious they're looking for a strong recommendation. So when you come out of an effort like this, they're looking for more than just those little interesting insights. They're really wanting to know, hey, how much do you recommend? How much paint booth, how much sanding, wash bay, how big do these buffers need to be? They're wanting pretty concrete answers so that they can go forward and go cost out what those options might be.
Yeah, I was saying, I think that's usually depending on each audience, each have certain things that they're looking for, but obviously these are pretty sizable decisions to be made. So want those to be, I'm sure they were one of those to be rooted in some deep insights, but good perspective. And looks like we have one more here. Looks like lengthy one, so let's see how I do. All right. So, as a manufacturing modeler, what is the change management strategies that may be needed for variables that may be more difficult to adjust, and I'll say control, like rework rates, mean time to failure, versus inputs that may be more easily changed, like batching rules or operational strategies?
Yeah, that yeah, that it's from an architect, it seems like an architecture type question, right? So how do I set this model up in such a way that um, the things that can be changed easily or want to be tested, I set up in a way that so that the model can update those fairly easily. For us, number of pieces of equipment um, tend to be one of those properties that we set up in our models. Um, uh, Rework rates in this case were done uh, as an input as a description about the part, and so we would have had to. We didn't really. Each part had a different rework rate, um, and so having to do testing around that required some additional challenges. Uh, Meaning we had to change our input tables and go one step at a time. So what we find in this industry is that connecting to live data isn't really advantageous. The data is really messy, um, and you may not be able to uh, uh, clean it in a way that you'd want it tied just directly. You'd want to have a way to review that data ahead of time. I don't know if that is exactly what they're talking about, but yeah, to me, this seems like an architecture type question. You want to make sure you set up your models in such a way that you can make the changes and test the things that you need to test easily.
Yeah, so to me, it seems like rework rate, mean time to failure are things that seem more systemic to the organization. If it's more difficult to improve the reliability of an asset than it is to change a policy. But so it seems like there's the actions you can take would vary depending on the level of recommendation. But yeah, a lot some different thoughts there. But looks like that's about it for questions. Chris, want to thank you once more for the great presentation. So a lot of good questions that came in as well. So appreciate your industry expertise and really appreciate the time here today.
Yeah, thank you very much for having a user conference. This is fantastic. I want to echo Olivia's points that she made about networking. Um, in 2019, I also presented at uh, Simio Sync, and it turns out Olivia and I actually sat next to each other. So it's pretty interesting. We were presenting next to each other as well. So yeah, great community, great opportunity to network, and hope folks can make the most of it.
Things find a way to come full circle. But with that, I want to thank the audience for participation today, and I had a great day one, and looking forward to day two.